Okay, could somebody confirm you can hear me?
Yeah,
Thank you. Let me share my screen. It's not very useful, but I'm sharing my screen. I don't need that either. All right, before we begin, there's two things I need to add to you guys to tell you about the unknown project. And the first is how to read the table. I'm not sure I mentioned what the different symbols on this unknown list table, the name of this file is unknown list sp20.xls. This is the unknown list of the unknown species. And I'm not sure I informed you guys how to read the table. So let me do that now. Let me blow that up a little. When you're coming on here, I think you know what a plus means. That means for this test, the results are positive. And if it's negative, the results are negative. The V, however, means that the results are variable. Did I discuss that? Anyone?
I don't think you discussed it directly, but I kind of
Okay.
gathered it from what you talked about.
Okay, thank you. I thought I did not, so that's why I wanted to make sure. It does say down here what the symbols mean, and a V means variable. So that means if you request a test and you get a result back and you look on the table and it says V, that means you must take that as either a plus or a minus. So you have to consider both options. So that this species, let me get the species shown, Enterococcus faecalis, is both positive for, what is that test? Gelatin hydrolysis. So if you're looking at gelatin hydrolysis positive, that'll be these species here. And the V counts. On the other hand, if it is gelatin hydrolysis negative, the V also counts. And so it would be these species under consideration now. So the V would count and all the negatives count. Any question about the V? And ND means no data. You can scroll down to that. And that means, or not determined, no data, not determined, same thing. It means that we don't have any data to put in this cell here. This test, urease, is not normally done on Enterococcus faecalis. So we have no data to put into this cell. That should be treated like a variable. So if you're trying to determine the results here and your results are positive, then you should include all of these positives here. This is a little slower because of the way they have the highlighting working. It hides every time, so I got to click on there to make it show again. It used to not be that way. So
Dr. Volpe,
you must include what?
there's a little pin to the right of your, so where you're at right now, if you go all the way to the right of the screen
A pin?
and click that pin, that should pin the taskbar. Click that.
Okay, thank you.
Yep.
All right. So when you're including the pluses here, you must include the ND also. And the same with the negatives. When you're considering the negatives, you must consider the ND as a potential negative. All right. Some of these tests are not ever used on any of the species, like actually both of these, PR inulin and the growth on EMB. They're never done on the gram negatives. So we have no data for the entire list of species we have there. And you'll notice that some of them, like this one here, there's only 2 that we have data on, and then the others are no data. And hopefully you've narrowed it down to these 2, and then this test can help you. But otherwise, doing this test early would not be a good idea. All right, any questions about this table? Let me briefly mention with the PR glucose, PR lactose, PR sucrose, and PR mannitol, and PR inulin, the A stands for acid. The sugar is fermented, and that produces an acid, changing the color to a yellow in the tube. And that we record as an acid. If, on the other hand, the fermentation does produce an acid, but also produces gas, we go AG. And for this table, you guys can ignore the parentheses. The parentheses means that most of them are AG, but some of them are A. And in our species, all of them will be as shown with the parentheses G. Okay? So you can treat the A parentheses G parentheses as AG. All right, any questions about this table? Oh, another thing I should mention, the PR glucose, the PR lactose, the PR sucrose, the PR mannitol, and the PR inulin will not be shown in the list of unknown tests. If you come up here and take a look at the unknown tests, you will not find them. Week 5 lab unknown test, they will not be there. Instead, they're under PR carbohydrate because all of them are fermenting a sugar and all they have is a different sugar. So they're listed here under PR carbohydrate, and then you use this for each of the different sugars. Any question about that? And then the last thing I may have not mentioned is cellular growth arrangement. That's how the cells stick together. We talked about this in the lecture. For cocci, you can get singlet cells. There can be diplo cocci. There can be staphylococci. This is clusters. There can be streptococci. This is chains. There are other possible arrangements too, like Sarxinia, 8 cells. You cannot determine the cellular growth arrangement from the gram stain. In making the gram stain, we usually obtain the cells from a solid media, meaning you're growing the cells on a gelatin, not a gelatin, an agar plate. And the cells, when you pick them up from an agar plate, they're going to tend to stick together. And then when you smear them out over the water and let them air dry, they will also start to clump. And so clumping is very common in the gram stain. And then another thing is the gram stain, when you're making it, you're not being terribly gentle. And then the streaking around the cells tends to break the streptococci or the streptobacilli. And so the strepto, either cocci or bacilli, tend to be broken in the gram stain. So you cannot generally tell the cellular growth arrangement from the gram stain. To get the cellular growth arrangement, you have to grow the cells up in a liquid culture, a broth. And then you take the liquid and then you smear it over the slide. And then you let that air dry and heat fix it and then gently stain it with 1 dye instead of 2 in the gram stain, and then you're not adding iodine as well. But the point is, it's a more gentle procedure. You're getting the cells from a liquid culture, and then the cellular growth arrangement will show. So if you want to determine the cellular growth arrangement, you need to run the cellular growth arrangement test. You cannot get it from the gram stain. Any question about any of that? All right. That's it for the unknown project. I'm sorry I forgot to mention those to you. But I got it to you, so there you go. Let's go back home here, and now let's talk about the lab for today. Today is February 8th, and we're supposed to be doing lab 6, disc diffusion and antibiotics. Any questions about what we're going to do? I guess I'll leave that up for the lecture later. That doesn't look like I got the right one. Yeah, that is the right one. Sorry. All right. Lab 6. Disc diffusion, evaluation of disinfectants, antiseptics, and antibiotic effectiveness. In this lab, we're going to be mainly looking at the disc diffusion method, also called the disc diffusion assay, and most of the time it's called the Kirby-Bauer method, after the two scientists who invented it. It is a very good method for determining the resistance of cells to an antibiotic. And when clinicians are trying to determine whether a patient's bacteria cells are sensitive to one antibiotic, they'll run the Kirby-Bauer test on the bacteria that's causing the infection. And usually this is not done unless the patient is carrying a bacteria strain which is resistant to some or all forms of antibiotics. But like I said, sometimes it's done when they're trying to determine if there's any antibiotic which will be effective against the bacteria. And it's a very good test. However, this test can be used on in other ways, like it can be used to test the effectiveness of a disinfectant or the effectiveness of an antiseptic, and it can be used to test other ingredients. I once had a student come in, and for some reason I don't remember, but she was interested in, I think, various herbs. And she was testing the herbs to determine the antibacterial effect of the herbs. And if you don't know from history, and most of you probably don't, in the old days, long before antibiotics and before we had preservatives, I'm talking about like in the Middle Ages, a long, long time ago, people used various herbs to reduce the spoilage or make the food last longer before it would spoil. And she wanted to test the various herbs and maybe other spices that you add to see the antibacterial effectiveness. And I was surprised she actually found quite strong antibacterial effect of some herbs. I don't remember which ones they were, but I think parsley was one. And I know that cloves was one that they heavily used in the Middle Age to prevent meat from spoiling. So I know that one was one, but anyway, she did get very good results. And how she did that was she brought in those things and then did the Kirby-Bauer method. In today's lab, as normal, there's some reading to do before the lab. Please do the reading. We will have some video clips and a virtual lab today. The learning objectives for today's lab: be able to identify the type of chemical agent and the active ingredient used in various disinfectants and/or antiseptics. 2, evaluate the effectiveness of disinfectants and/or antiseptics using the disc diffusion method. And like I said, that's also called the Kirby-Bauer method. 3, determine the mode of action of various antibiotics. 4, evaluate the effectiveness of various antibiotics using the disc diffusion method. And this is mainly what this lab is going to be about, using the Kirby-Bauer method to evaluate the effectiveness of the antibiotics. 5, list variables that influence antibiotic diffusion susceptibility testing. 6, be able to define the terms, what's sterilization, disinfection, a disinfectant, an antiseptic, a bactericidal agent, a bacteriostatic agent, an antibiotic, what's a spread plate, and what is a zone of inhibition. Any questions about what we're going to do? All right. So in some terms, sterilization refers to the elimination of all viable organisms, and this does include endospores. Normally in the microbiology lab, when we give you sterile media, the reason why it's sterile is because it has been stuck in the autoclave. And that is usually how in the microbiology lab, we do sterilize most agents. I suppose it's possible you could say with the loop, the inoculating loop, we do sterilize that by putting it in the back to incinerator or a flame, but most of the things are sterilized in the autoclave. Disinfection refers to the destruction of vegetative cells, but not necessarily endospores. A disinfectant is a chemical agent applied to an inanimate object, like when you're using chlorine bleach to disinfect your toilet, the bleach is a disinfectant. On the other hand, an antiseptic is a chemical agent applied to living tissues. Usually, an antiseptic is less harmful and less irritating to the living tissue than an antiseptic, but that is not always the case. For example, I think I mentioned that an old treatment, it may still be used today, to treat necrotizing fasciitis was to put wrap the gauze in bleach and then put it on the necrotizing fasciitis. Certainly, the bleach there was used as an antiseptic, and I once had somebody I knew treat their cat with bleach to clean out the wound, and they were using bleach as an antiseptic. Obviously, bleach is fairly irritating to skin and tissue, but when you have necrotizing fasciitis, they would rather you deal with the bleach and have the bleach kill the agent causing the necrotizing fasciitis. They would also treat that with antibiotics given internally, but they were treating the necrotizing fasciitis externally with the bleach. If you don't know, necrotizing fasciitis is, what is that called? The skin eating disease? Is that what it's called? Does anyone remember? Sorry.
Yeah, flesh eating.
Flesh-eating bacteria. There we go. Flesh-eating bacteria. So when you have an infection with a flesh-eating bacteria, at least the old treatment was putting gauze on with bleach in it. Like I said, I don't know if it's still done today, but it was done. Gosh, that's a long time ago, in the 1980s, maybe the 1990s as well. And I don't know if it's still done, but it used to be done. To evaluate the effectiveness of chemical agents, the surface of a nutrient agar plate is inoculated with a particular bacterium. Usually you grow that bacterium in a lawn of bacteria where the bacteria will be growing everywhere. Paper discs then saturated with different chemical agents are then applied to the surface of the agar. The chemical agent diffuses into the agar medium, establishing a concentration gradient around the disc. You then incubate the plates overnight at 35 degrees and look at the bacterial growth pattern around the disc. If there is no zone of inhibition, meaning an area of no bacterial growth around the disc, you can assume the chemical is ineffective. If there is a zone of inhibition around the disc, then the chemical is at least a little bit effective for that particular bacterium. However, that does not mean that that bacteria is sensitive to that agent. It just means that that agent is killing bacteria, at least to some degree. Okay? Any question about that? All right, here's a table showing you the different chemical agent, like the alcohols. Generally, they're used as an antiseptic, and they're a very weak antiseptic. So most of the time, we call them a degerming agent. Like when we apply an alcohol swab to the skin before they give a needle injection at the site they've swabbed, you don't remove all of the bacteria from the region you swab. All you do is reduce the number of bacteria, reducing it to a low enough number that is fairly safe to give the injection. Okay? And that's why we call it a degerming agent. Aldehydes like formaldehyde, formalin, and glutaraldehyde are a disinfectant. This is a rare disinfectant that actually kills endospores. There are really only two groups of disinfectants that kill endospores. I'll talk about the next one now, and that's the peroxygens like hydrogen peroxide. They're a very good antiseptic, and they do kill endospores. I don't know why that's not in there, but hydrogen peroxide does kill endospores. Hydrogen peroxide is found in every, well, most homes, okay? Formaldehyde, formalin, and glutaraldehyde. I don't think many homes have any of those. Halogens are actually found in your home, like tincture of iodine is used as an antiseptic. Chlorine bleach is used as a disinfectant. So those are two halogens. Heavy metals are something that for a long time was not used by the healthcare industry. However, their use has come back, and that's because of the development of antibiotic resistance, because various bacteria have developed the resistance to antibiotics. We brought back the use of heavy metals, like when they treat gauze on a wound with a heavy metal. The heavy metal will prevent bacteria from growing in the wound. Heavy metals can also be used as a disinfectant, but in the medical industry, like I said, the use of heavy metals has come back. For many years, they were not using heavy metals because heavy metals are toxic. You do not want to get heavy metals internally, meaning consume it, because it is a toxic. And there were better agents, like antibiotics, but because of the development of drug resistance, heavy metals use has come back. Hyperoxygens I've already talked about. Phenolics, this is actually what Joseph Lister first used when he was doing surgery, antiseptic surgery. He used phenol as his antiseptic agent. And phenol was not a very good antiseptic, by the way. It was very toxic to the skin or irritating to the skin, had a very unpleasant odor, and it would actually corrode surgical metal instruments as well. Surface active agents are like soaps and quaternary ammonium compounds used as a disinfectant, mainly used to clean down surfaces. All right, the zone size of inhibition will depend only partially on the sensitivity of the organism to the disinfectant or antiseptic. There are other factors that affect the size of the zone of inhibition, including the concentration of the chemical. Generally, if the chemical is more concentrated, you'll get a larger size to the zone of inhibition. The molecular weight of the agent also affects it. Generally, the smaller the chemical, meaning the smaller the molecular weight of the chemical, the larger the size of the zone of inhibition. And if you think about it, it's just because a smaller chemical agent is going to diffuse quicker and more rapidly through the agar than a larger molecular weight agent. And then the density of the bacterial inoculum can also affect the size of the zone of inhibition. Generally, the more dense the bacteria, the smaller the size of the zone of inhibition. Any question about any of that? So evaluating antibiotic effectiveness, antibiotics are categorized as bactericidal if they kill the susceptible bacteria, and they are called bacteriostatic if they inhibit the growth of bacteria. Inhibiting the growth of the bacteria does not kill the bacteria. So once you remove the bacteriostatic agent, the bacteria may continue to grow. When a bacteriostatic antibiotic is used, it's relying on the immune system to assist in the elimination of the infection. Any question about any of that? All right. The Kirby-Bauer diffusion test is the most common method used for testing antibiotic resistance or susceptibility. So when you're doing an antibiotic test, they're most likely going to do it on the Kirby-Bauer, use it on the Kirby-Bauer diffusion test. The results of such tests help physicians choose which antibiotics to use when treating a sick patient who has a bacterial infection. Bacteria are isolated and then grown on an agar plate. And usually when we grow it on the agar plate, we grow it as a lawn of bacteria where the bacteria will grow everywhere on the plate. Let me blow this up so you can see that plate a little better. So other than the zones of inhibition, we have bacteria growing everywhere on the plate, while the plate is slight white in appearance. And the clear zone there is no bacteria in the zone of inhibition. I've got to shrink that down a little further. So bacteria are put on the plate, and then filter disc impregnated with an antibiotic is applied to the surface of the agar. The antibiotic will diffuse out of the paper disc, and if the antibiotic is effective at inhibiting the growth or killing the cells, you'll see a zone of inhibition after you get the bacteria to grow. So there will be a concentration gradient around the disc, and the zone of inhibition is where the antibiotic concentration is high enough to inhibit the bacterial growth or kill the organism, one or the other. Or maybe both. The inhibition zone size is dependent on several factors. Obviously, it is dependent on the sensitivity of the bacteria to the antibiotic. It is dependent on the diffusion rate of the antibiotic. The smaller the antibiotic, the more it will diffuse, and then the larger the size of the zone of inhibition. The growth rate of the bacterium will also make a dependence on the size of the zone of inhibition. Let me see if I can remember that one. If the bacteria grow faster, I think it's a smaller zone of inhibition, as opposed to if the bacteria are growing at a slower rate. Anyways, the point is there's a lot of variables that can affect the size of the zone of inhibition. And so when we do the Kirby-Bauer test, we have to standardize the variables. And Table 6.2 lists the procedure protocol required to standardize the variables when performing the Kirby-Bauer diffusion test. 6.2, you inoculate the nutrient broth using several bacteria colonies isolated on a non-selective media, meaning the plates must be non-selective. And the plates can be no longer than 24 hours old. we want freshly growing bacteria. So the bacteria are quickly growing. And then you inoculate the bacteria in a nutrient broth and you let it grow for no more than 24 hours, and you adjust the turbidity to 0.45 McFarland units. That'll be approximately 1 times 10 to the 5th bacteria cells per mil. You then inoculate at room temperature Mueller-Hinton agar plates. We always use Mueller-Hinton agar plates because the type of media can affect the size of the zone of inhibition. The Mueller-Hinton agar plates are always between pH 7.2 to pH 7.4 because the pH can also affect the size of the zone of inhibition. The agar is furthermore, the agar in the plate is always a depth of 4 millimeters deep. The deeper the agar, the slower the chemical or antibiotic can diffuse through the agar. So the depth of the agar does affect the size of the zone of inhibition. And then we always use plates of 150 millimeters diameter when using the Kirby-Bauer disc diffusion method. And what you do is you take the bacteria using a non-toxic swab, like a cotton swab, and then spread it over the plate, obtaining confluent growth of the bacteria on the plate, meaning you want the bacteria to grow in a lawn where it's growing everywhere on the plate. You then allow the plates to sit 5 minutes to allow the broth to be absorbed by the agar, and then you place the disc containing the antibiotics on the plate. No closer than 24 millimeters to each other. So the discs must be 24 millimeters apart, no more than 12 discs per 150 millimeter plate. And the antibiotic disc, like I said, had to be added 5 minutes after putting on the bacteria and no longer than 15 minutes after putting on the bacteria to the agar. You then incubate the plates no longer than 15 minutes after adding the antibiotic, and you put them in the incubator in a non-CO2 incubator for 16 to 18 hours to grow at 35 degrees Celsius. Obviously, if you were to grow them longer, the size of the zone of inhibition would be decreased. If you were to grow them for a shorter time, the size of the inhibition will be slightly increased. So we always grow them for 16 to 18 hours. Any questions about the standard protocol for doing the Kirby-Bauer test method? All right, so we use the standard protocol so that whoever is doing the test, assuming they're using the same antibiotic and the same bacteria, they should get very similar results in the sizes of the zone of inhibition for the different antibiotics, regardless of where they are in the world. After incubation, the inhibition zone sizes are then measured in their diameter using a millimeter. You then compare the measurement of the size of the zone of inhibition to the table set up by the National Committee for Clinical Laboratory Studies, and that's usually abbreviated NCCLS, to determine if the bacteria is considered sensitive, intermediate, or resistant to that particular antibiotic being tested. So there we have a bacteria, the Staphylococcus aureus, shown here. There is a zone of inhibition around an antibiotic disc. There's a ruler, and it looks like this is 20 millimeters in diameter. And then you take a look at that in the table, the NCCLS table. And for Staphylococcus aureus, for penicillin, I forgot to mention the antibiotic here is penicillin G. It says that if the zone of inhibition is 20 millimeters or less, it's considered to be resistant to this antibiotic. In the other hand, if the zone of inhibition were to be between 21 to 28 millimeters in diameter, the zone of inhibition states that it is intermediate to this antibiotic. And if the size of the zone of inhibition were to be equal to 29 millimeters or greater, then we say this antibiotic is sensitive, excuse me, this bacteria, Staphylococcus aureus, is sensitive to this antibiotic. And that's how you interpret how a strain is sensitive or resistant or intermediate to this antibiotic. You measure the size of the zone of inhibition, and then you compare it to the NCCLS table. Each species will have a different measurement for resistance for each antibiotic in the table. Any question about any of that? So it's 20 millimeters or less for Staphylococcus aureus, but Staphylococcus epidermidis may be different for the size of the resistance for penicillin G. And of course, with a different antibiotic, it usually is a different size for the same organism. Any question about that? So that's how you determine if a species is sensitive or resistant to a given antibiotic. You have to grow it up on the Kirby-Bauer diffusion method, measure the diameter of the zone of inhibition, and compare it to the NCCLS standards. You cannot simply look at it and say, oh, that's a big zone of inhibition. That's a small zone of inhibition. So it's sensitive to this one, resistant to that one. You cannot do that because we don't know, for example, the size, the molecular weight size of the antibiotic. If this is a huge antibiotic, and that's a very small antibiotic, we expect the zone of inhibition to be larger here than for here. Any question about any of that? If not, know the terms of this lab. Don't need to look at the references, but you should know the terms. We're not going to be physically performing any of these activities because everything's going to be done online, but you will be held responsible for how to interpret the effectiveness of antibiotics using the Kirby-Bauer diffusion method. We have a video clip for you to watch on preparing a spread plate. This is talking about how to prepare a spread plate, and let me demonstrate that for you. And then review the steps for using aseptic technique when preparing a spread plate. First, let me get something I can open. So let's pretend this is my tube. I don't have any test tubes. I don't have a cotton swab here either. So pretend this is a cotton swab. Can you guys see this? Anyone?
Yeah, if you hold it right there, we
If I
can.
put it right in front of my face, you can see it. Okay, what you do is you put the cotton swab in the tube. Obviously it's sterile and you grow up the bacteria. Cotton swab is sterile. And you pick up the liquid on the tube. And then you touch the tube to the edge of the tube. To say that right, you touch the swab to the edge of the tube to get the worst of the liquid off. You don't want the swab to be dropping liquid onto the plate. You get the worst of it off by touching it. And you can kind of squeeze a little bit too. Then you take your plate and your cotton swab, and this is a sterile agar plate with nothing on it. And then, I don't know if you can see this, you swab everywhere on the plate. Then you take the swab and you turn it a quarter of a turn. You take the plate and you turn it a quarter of a turn. And then you take the swab and you swab the plate everywhere on the plate. And then you take the swab and you turn it a quarter of a turn. You take the plate and you turn it a quarter of a turn. And then you swab once more everywhere on the plate. The reason for doing this is to get the bacteria to grow everywhere on the plate in a lawn of bacteria. I once had a student who took a swab and did something like that, okay? She had huge holes in the plate without any bacteria. And then she brought the disc, put the disc on, and then brought the plate to me and said, how can I measure the size of the zone of inhibition? And I looked at this and said, you don't have the bacteria growing on a lawn. You got humongous holes of bacteria not growing on the plate. So there's no way to measure the size of the zone of inhibition. And I told her she didn't streak it well and she would have to do it again, or she could use her lab partner's plate. So you do need to get the bacteria to grow everywhere on the plate. And then when you're all done, you take the cotton swab and you go around the edge of the plate. The reason being is that when you're doing the swab like this, occasionally you'll miss a gap near the edge. And so you take the swab and go around the edge of the plate so that you get the bacteria growing everywhere. And you do that swabbing 3 times to get the bacteria to grow everywhere. And then you let the plate sit for 5 minutes so that the liquid containing the bacteria will be absorbed by the agar. And then you put the paper disc containing the antibiotics down. And before 15 minutes after putting the bacteria on, you should have all the paper discs down on the plate. And then you should incubate the plate no longer than 15 minutes after you put the paper disc containing the antibiotics on the plate. And what you do is you turn the plate, get the lid on, turn the plate upside down, and then grow it in the incubator for the appropriate time. It's about 16 hours. I think it's 16 to 18 hours at 35 degrees temperature. Any question about that? All right. Procedure 2, view the following video clips. Preparing a culture for Kirby-Bauer disc diffusion. Watch that video. And then 2, a video on interpretation of the results of the Kirby-Bauer disc diffusion test. And then we have a virtual lab for you to run. Come on. There we go. This may take a little while to download. I have a fairly fast internet connection, so it doesn't take too long. Why did that only come up to there? Not sure. All right, you need to hit start, but you can read the description, the steps, and the credits I wouldn't look at. But you can hit start, and it'll now show you a Kirby-Bauer disc diffusion test that's been ran, set up, and grown. And what you do here is you got zones of inhibition. That one I'll do because that one I know. S stands for streptomycin. And you take the ruler and you bring it over here, putting the 0 there, and you measure the size of the zone of inhibition. Looks like it's there. So that looks like about 19 millimeters in its zone of inhibition. So streptomycin 19 millimeters will be here. And if it's green, that means it's correct. If you take it and you read it wrong, you say, oh, well, that looks like 2. That's centimeters, by the way, not millimeters. And so you go here. It'll give you an X, meaning that's the wrong answer. You go there, that's the wrong answer. You go there, it's the correct answer. TE is tetracycline. That looks like about 18 millimeters. Let's guess wrong. I think that's wrong. I'm right. It's 18. All right. So, like I said, if it's correct, it'll be green. And you can just do this to measure the sizes of the zone of inhibition. And then it tells you up here, this table, I can't really read it, but maybe I can blow this up. This row is the size of the zone of inhibition for this species is resistant to the antibiotic. This row means this species is sensitive to that antibiotic. And that one means they're intermediate. Let me shrink that down. You'll need to do this 3 times. Click the menu button and then the restart again, and it'll switch the bacteria here. So here we have Pseudomonas aeruginosa. And there's one you could measure. And then you can do it again. We have 3 different plates here. Staphylococcus aureus here, Pseudomonas aeruginosa, and I think the third one was E. coli. The first one, yeah, I got it right. So you can do this for these 3 species and determine the antibiotic sensitivity. You'll need to do this to answer some of the questions in the worksheet for today. Any questions about that? I'll leave that up in case there's a question. All right, using the standards required for the Kirby-Bauer susceptibility testing, an E. coli culture is prepared using a spread plate technique. Antibiotic discs are placed on the surface of the agar and it's incubated overnight at 35 degrees. Below are the results of the zones of inhibition, as well as the NCCLS zone standards used for interpretation. So there's the zone of inhibition, and we're measuring that with a caliper. How you measure with the caliper is not from here to here, so don't read that as close to 10 millimeters. You'll note from here to there, that's not marked. The 0 is starting here. So to read a caliper, you read from 0 to 0. So this would be about 15 millimeters there. And I'll do the first one for you. Let me shrink this down a little. So for ampicillin, that's the antibiotic. And remember, the bacteria is E. coli, so we use this table. The size of the zone of inhibition is 15 millimeters. Come and take a look at that at the table. I'm surprised I have that up there, but well, that's not right. It's intermediate. 15 millimeters is intermediate. So the point is, write down the size of the zone of inhibition. You have to measure that using the caliper and then give the interpretation. Take this 15 millimeters up for ampicillin, and you see that it's in the eye. So mark it I. Remember, I is intermediate. S, sensitive to that antibiotic, and then R, resistant to that antibiotic. Any question about any of that? So do that on the worksheet and submit only the worksheet. I've got the worksheet here someplace. There it is. 15 millimeters. And like I said, you can mark that with an I. Do that for the others. Cephalothalenthin. I have trouble saying that. SF. Right here. Gentamicin and tetracycline. Remember to use the E. coli table because this bacteria here is E. coli. 3, list the 5 variables that must be standardized when performing the antibiotic susceptibility test using the Kirby-Bayer diffusion method. 4, the size of the zone of inhibition often varies for 2 different species of bacteria when challenged with the same antibiotic. What is a possible explanation for these differences? 5, what would happen if we didn't use aseptic technique to put antibiotic disc on the plate? And you should mention what will happen to our test results. 6, what would happen if we increased or decreased the concentration of the antibiotic in the disc? Be specific in your answer. And you must answer for both what will happen when we increase the concentration in the disc and what will happen when we decrease the concentration in the disc. If you only answer it for one, you'll only get partial credit. 7, antibiotics can be bactericidal. That means they kill the microbe, or they can be bacteriostatic. That is, they inhibit the microbial growth, but do not kill the organism. And if it's bacteriostatic, if you then remove the agent, the bacteria, if it's still alive, may grow. When observing a zone of inhibition around the disc, how would you determine whether the antibiotic causing the zone was bactericidal or bacteriostatic? I'm going to warn you that this is a thinking question. You cannot get the answer just by looking it up in the lab manual. You have to think about it. And most of the time, most students get this question wrong the first time. Some terms, I've had no student get this one right the first time, but usually the second time, most students, meaning the second grading the lab, most students will get it correctly. So this is a tough question. You do need to think about it. Sometimes I can get close to half the students getting it correct on the first time. Like I said, you have to think about it, and it is a thinking question. So think about this one. Don't just write down what you think is the right answer. Think about it. All right, 8. When performing antibiotic sensitivity testing, it's important that the test conditions are kept very standardized. Like we always grow it on the same kind of media, Mueller-Henton. We always have the same agar depth, 4 millimeters. We always use the same age of the culture. Cultures that have been growing less than a day. I don't remember how long exactly, but something like that. And then why? A 9. Are there any other substances besides antibiotics we could use and evaluate using this method? Okay. This is a slightly thinking question, but this one you can look up in the lab manual. So that one's actually an easy question for most students. 10, does the presence of a zone of inhibition necessarily mean that the bacterium being tested is sensitive to the antibiotic? And then explain your answer. 11, from the size of the zone of inhibition of chloramphenicol on E. coli in the virtual lab, is the bacteria sensitive, intermediate, or resistant to the antibiotic? And then for chloramphenicol on Pseudomonas aeruginosa is the bacteria sensitive, intermediate, or resistant to the antibiotic. All right, there you are. Are there any questions? If there's no questions, go ahead and work on the lab. I will be here until, what time is it now? Close to 4 o'clock. I'll be here until 4:30 to answer questions. But at 4:30 or when the last student logs off, I'll also log off.
Thank you.
All right, so work on the lab.
Thank you.
You're welcome. Yeah, I'm gonna step away from my computer for a little bit, but I'll be right back.